Good morning to everyone. This is Dr. Sailaja, working as Associate Professor of Mathematics, MLR Institute of Technology, Hyderabad. In the last class, we have discussed about various types of real matrices and their properties. Today, in this class, we are going to discuss about various types of complex matrices and their properties, and theorems on real and complex matrices, and as examples on real and complex matrices. So, before going to define a complex matrix, what is a complex number and its a form? So, let the complex number is denoted by Z is equal to A plus IB, where A and B are real numbers, and A is real part and B is imaginary part. So, this complex number A plus IB is denoted by Z, and the conjugate of a complex number. Suppose we take a complex number Z is equal to A plus IB, and we denote the complex conjugate, that is conjugate of a complex number is denoted by Z conjugate or Z bar, and it is defined as A minus IB. That means we are changing the sign of imaginary part. Suppose the given complex number Z is equal to A minus IB, then the complex conjugate or the conjugate of a complex number is Z bar is equal to A plus IB. That means A plus IB is conjugate of the complex number A minus IB, and A minus IB is conjugate of the complex number A plus IB. That means just change the sign of the imaginary part. That is a conjugate of a complex number. Now coming to complex matrix, the matrix contains complex numbers in any row or column is called a complex matrix. Now this is a conjugate of a matrix. Suppose the matrix A equal to Aij of order m by n, and A conjugate, that is we write all the elements of the matrix A are conjugate elements is called the conjugate of the matrix. Suppose the matrix A is 1 plus I, 2, 3 minus 2i, 4, 5 minus 2i, I minus 1, 5 minus 4i, minus 7, 0. So, this is a given complex matrix. Since this matrix contains the complex numbers 1 plus I, 3 minus 2i, 5 minus 2i, 5 minus 4i, and these are all complex numbers. That's why this is complex matrix. Now, we find the conjugate of this matrix and it is denoted by A bar, conjugate. That means here the first element is 1 plus I, and the conjugate of 1 plus I is 1 minus I. That means we change the sign of the imaginary part 1 minus I. Similarly, 3 minus 2i is a complex number, and the conjugate of this complex number is 3 plus 2i. So, this is a conjugate of the complex number 3 minus 2i. Similarly, 5 minus 2i is complex number, and its a conjugate is 5 plus 2i. I minus 1. The conjugate of this element is minus I minus 1. 5 minus 4i. The conjugate of this element is 5 plus 4i. So, that's why this matrix A bar is the conjugate of the given matrix A, and it is denoted by A bar. A bar means the conjugate of the given matrix A. Now, we define the transposed conjugate of a matrix. Suppose the matrix A equal to Aij be any given matrix, then the transpose of the conjugate of A is called transposed conjugate of A, and it is denoted by A star or A power theta. That means first we perform the operation transpose and then conjugate, or we can find the first conjugate and then transpose. In any order we can find the complex conjugate and transpose of the given matrix. So here the given matrix A equal to 1 plus I, 2, 3 minus 2I, 4, 5 minus 2I, I minus 1, 5 minus 4I, minus 7, 0. So this is the given matrix. Now we find A star, or A star is the conjugate transpose of the given matrix A, that is A bar whole transpose. A bar whole transpose. Now first find the conjugate of the complex elements, that is 1 plus I. Conjugate of 1 plus I is 1 minus I. 3 minus 2I is 3 plus 2I. 5 minus 2I is 5 plus 2I. 5 minus 4I is 5 plus 4I. So this is a conjugate of the given matrix, that is A bar conjugate. 1 minus I, 2, 3 plus 2I, 4, 5 plus 2I, minus I, minus 1, 5 plus 4I, minus 7. Here minus 7 is a real number, so the conjugate of the real number is itself only 0. So this is the conjugate of the given matrix A. Now we find the transpose of the conjugate matrix, and it is denoted by A bar whole transpose. That means transpose means interchange the rows and columns. So first column is 1 minus I, 4, 5 plus 4I, 2, 5 plus 2I, minus 7, 3 plus 2I, minus I, minus 1, 0. So this is A conjugate transpose. Now here A conjugate transpose, it is also denoted by A power theta. Simply it is denoted by A power theta. So this is A conjugate transpose of the matrix. Now we see different types of complex matrices. Now the first one is Hermitian matrix. So what is the definition of a Hermitian matrix? Suppose the matrix A is a given matrix. If A star equal to A star means A conjugate transpose equal to A. If this property is satisfied, then the given matrix A is said to be Hermitian matrix. Take an example. A equal to 1, 2 plus 5I, 3 minus 2I, 2 minus 5I, 5 minus I, 3 plus 2I, I, 0. So this is a complex matrix. Now we verify whether this given matrix A is Hermitian or not. So first we find the conjugate of the given matrix, that is A conjugate. 1 is real number, so the conjugate of a real number is itself. 2 plus 5I, conjugate is 2 minus 5I. 3 minus 2I, conjugate of 3 minus 2I is 3 plus 2I. 2 minus 5I, it is also a complex number, so the conjugate is 2 plus 5I. 5 minus I is a complex number. Here the real part is 0. So minus I is also written as 0 minus I. So the conjugate of 0 minus I is I. 3 plus 2I. 3 minus 2I is conjugate. I minus I is conjugate of I. 0. So this is A conjugate or conjugate of the given matrix A, and it is denoted by A bar. Now find the A transpose. A conjugate transpose or transpose of A conjugate. So interchange the rows and columns. 1, 2 plus 5I, first row. 3 minus 2I. First column elements becomes first row. Second column elements 2 minus 5I, 5 minus I, 3 plus 2I, I, 0. Now, observe the given matrix and conjugate transpose of the matrix. If these two matrices are equal, then we can say that the given matrix A is Hermitian matrix. Now, the first row elements are 1, 2 plus 5i, 3 minus 2i. Second row elements are 2 minus 5i, 5 minus I. And third row elements are 3 plus 2i, I, 0. So, both the matrices are same. A and transpose of A conjugate. Both the matrices are equal. Therefore, the given matrix A is Hermitian matrix. So, the property of a Hermitian matrix or the definition of a Hermitian matrix is A conjugate transpose equal to A, or simply we can denote A conjugate transpose as A power theta or A star or A power theta. So, this is the symbol or notation of A conjugate transpose of the matrix. Now, we see the next definition of a skew Hermitian matrix. So, the property of a skew Hermitian matrix is A star equal to minus A. If this property is satisfied, then we say that the given matrix A is said to be skew Hermitian matrix. So, again, we know that A star is a transpose of A conjugate equal to minus A. Then we say that the given matrix A is said to be skew Hermitian matrix. Now we take an example. A equal to 5i, 2 plus 5i, 3 minus 2i, minus 2 plus 5i, 0, minus I, minus 3 minus 2i, minus I, minus I. That means this matrix contains complex elements. So that's why this is a complex matrix. Now first we find the conjugate of the given matrix A bar. 5i. Conjugate of 5i is minus 5i. 2 plus 5i. 2 minus 5i. 3 minus 2i. 3 plus 2i. Minus 2 plus 5i. Minus 2 minus 5i. 0. Minus I plus I. Minus 3 minus 2i. Minus 3 plus 2i. Minus I. Minus I. Now this is conjugate of the given matrix A. Now we find transpose of conjugate matrix, that is A conjugate transpose. Transpose means interchange the rows and columns of conjugate matrix. So minus 5i, minus 2 minus 5i, 3 plus 2i, these are the first row elements. Now write these elements in the first column. Minus 5i, 2 minus 5i, 3 plus 2i. Second row elements, minus 2 minus 5i, 0i. Now write these second row elements in the second column. Minus 2 minus 5i, 0i. Now third row elements are minus 3 plus 2i, I. Write these elements in the third column. Minus 3 plus 2i, I. So this is A conjugate transpose. Now observe the given matrix A and A conjugate transpose as 5i, that is minus 5i, 2 plus 5i, minus 2 minus 5i, 3 minus 2i, minus 3 plus 2i, minus 2 plus 5i, 2 minus 5i, 0, minus I, minus 3 minus 2i, so 3 plus 2i, minus I, and minus I. So this is exactly minus A. So here the property A conjugate transpose is equal to minus A. So this property is satisfied. So that's why the given matrix A is said to be skew Hermitian matrix. So Hermitian matrix is A star equal to A, that is A conjugate transpose equal to A, and skew Hermitian matrix is A conjugate transpose or A power theta or A star equal to minus A, then that is skew Hermitian matrix. Now coming to unitary matrix. So the definition of unitary matrix is A star A equal to I or A star equal to I. I is identity matrix. A star is conjugate transpose of the given matrix A. So A star into, that means the product of the given matrix and conjugate transpose is in identity matrix. If we get identity matrix, then we say that the given matrix A is said to be unitary matrix. So take an example, A equal to 1 0 0 0 0 minus 1 1 0 1. So this matrix is unitary matrix. That means find A conjugate whole transpose into A. Then you will get 1 0 0 0 1 0 0 0 1. So that's why the matrix A is said to be unitary matrix. So these are different types of complex matrices. Now we see a very important theorem on a real matrix, that is, every square matrix can be expressed as the sum of symmetric and skew symmetric matrix uniquely. So we take the first part, part 1. We take any square matrix A and it can be expressed as a sum of a symmetric and a skew symmetric matrix. This is part 1, and part 2 is this representation is unique. So the first part is we write the matrix A, that is A is any square matrix. A is any square matrix, then A can be written as 1 by 2 into A plus A transpose plus A minus A transpose. So here we add and subtract A transpose. So again we will get the matrix, the given matrix A itself. So 2A by 2 means A. So A equal to 1 by 2 into A plus A transpose and plus A minus A transpose. So separate the terms as 1 by 2 into A plus A transpose plus 1 by 2 into A minus A transpose. Let this matrix is denoted by B and this matrix is denoted by C. So where B equal to 1 by 2 into A plus A transpose and C equal to 1 by 2 into A minus A transpose. Now we prove that B is symmetric matrix and C is skew symmetric matrix, and this B plus C is, then we say that the square matrix A can be expressed as sum of symmetric and skew symmetric matrices. So first we prove that B is a symmetric matrix. So what is the definition of a symmetric matrix? If A transpose equal to A, then we say that A is symmetric matrix. A is symmetric matrix. So similarly, we have to prove that B is a symmetric matrix. So B symmetric matrix means find a transpose of the matrix B, that is B transpose equal to 1 by 2 into A plus A transpose whole transpose. That means we are finding the transpose of the matrix B. So 1 by 2 is a real number. So 1 by 2 into A plus A transpose whole transpose. And we have a property of the symmetric matrix is A transpose whole transpose equal to A. So here A transpose 1 by 2 into A transpose plus A transpose whole transpose equal to A. Apply this property of the transpose matrix. A transpose plus A transpose whole transpose is A. So here 1 by 2 into A plus A transpose or A transpose plus A, it is given as B only. So B transpose equal to B. 1 by 2 into A plus A transpose. Similarly, we have to prove that, so B is symmetric. We have to prove that C is a skew symmetric. So find a C transpose. Skew symmetric definition is C transpose equal to minus C. Then we say that C is skew symmetric. So find C transpose. C equal to 1 by 2 into A minus A transpose. So take the transpose of this matrix 1 by 2 into A transpose minus A transpose whole transpose equal to A. So A transpose minus A. Take minus common, then you will get 1 by 2 minus 1 by 2 into A minus A transpose If you take minus common, then 1 by 2 minus 1 by 2 into A minus A transpose. So this is 1 by 2 into A minus A transpose is C. So it becomes minus C. If C transpose equal to minus C, then we say that C is skew symmetric matrix. That means in part 1, we proved B is a symmetric matrix and C is skew symmetric matrix. So what is A? A can be written as sum of symmetric matrix and skew symmetric matrix. B is symmetric and C is skew symmetric matrix. So the part 1 is completed, that is, every square matrix can be expressed as sum of symmetric and skew symmetric matrix, and this representation is unique, that is part 2. So uniqueness part. So suppose take the another representation of a square matrix as A equal to P plus Q. So where P is symmetric and Q is skew symmetric matrix. So the definition of a symmetric matrix is P transpose equal to P and Q transpose equal to minus Q. Now A transpose, what is A? A equal to P plus Q. What is A transpose? P plus Q whole transpose. Now P transpose plus Q transpose, where P transpose is P and Q transpose is minus Q. So A transpose equal to minus P minus Q. A transpose can be written as P minus Q. Now in the first part we take that B equal to 1 by 2 into A plus A transpose. Now take the matrix B 1 by 2 into A plus A transpose. So here 1 by 2 into, here A is P plus Q and A transpose is P minus Q. So P plus Q plus P minus Q. We will get 2P by 2, that is P. So B equal to P. That means even we have taken another representation of the square matrix as P plus Q. Again we got P equal to B only. P equal to B. Similarly, we have taken C equal to 1 by 2 into A minus 1 by 2 into A minus A transpose. A minus A transpose is C. Now, C equal to 1 by 2 into A transpose is P minus Q and A is P plus Q. So, we get C equal to Q. So, what is C? C is a skew symmetric matrix and Q is also a skew symmetric matrix. So C equal to Q, B equal to P. So the representation of the square matrix is unique. So therefore every square matrix can be expressed as sum of symmetric and skew symmetric matrix uniquely. Now we take an example of this theorem. This is a given matrix A, that is minus 1, 7, 1, 2, 3, 4, 5, 0, 5. So this is the given matrix A. Now express this matrix into sum of symmetric and skew symmetric matrix. So A is the given matrix. We know that symmetric matrix, every square matrix can be expressed as sum of symmetric matrix and skew symmetric matrix. This already we proved in the previous theorem, that is, so we take a symmetric part of A is 1 by 2 into A plus A transpose. So here 1 by 2 into, here A is a minus 1, 7, 1, 2, 3, 4, 5, 0, 5 and A transpose is, transpose of the matrix is minus 1, 7, 1 first column, 2, 3, 4 second column, 5, 0, 5 third column. So A plus A transpose in by 2. That means this is minus 1, 9 by 2, A plus A transpose, that is minus 1, 9 by 2. This is the resultant matrix of A plus A transpose by 2. So this is a symmetric part of the matrix A. Now find the skew symmetric part, that is 1 by 2 into A minus A transpose. So this is a matrix A and transpose of the matrix A transpose is this. Now find A minus A transpose. by 2. So this is the resultant matrix of A minus A transpose by 2 is this. Now add these two matrices, that is 1 by 2 into A plus A transpose plus 1 by 2 into A minus A transpose. Then we get the given matrix, that is minus 1 plus 0. 9 by 2 plus 5 by 2. 7. 3 minus 2. Similarly 2. 9 by 2 minus 5 by 2. Next 3 plus 0. 2 plus 2. 3 plus 2. 2 minus 2, 5 plus 0. So this is symmetric part of the given matrix and this is skew symmetric part of the given matrix. So every square matrix can be expressed as uniquely sum of symmetric and skew symmetric matrices. So another theorem on complex matrices is every square matrix can be expressed as the sum of Hermitian and skew Hermitian matrix uniquely. The proof is same as above. Here also we take the square matrix A and it can be written as 1 by 2 into A plus A star plus A minus A star. So add and subtract A power A star and A star. A star is conjugate of the transpose matrix. So A equal to, we define or let us assume that the matrix A equal to 1 by 2 into A plus A star plus A minus A star. Now 1 by 2 into A plus A star plus 1 by 2 into A minus A star. So the matrix A we defined like this. Now we have to prove that part 1 is to prove that 1 by 2 into A plus A star is Hermitian matrix and 1 by 2 into A minus A star is skew Hermitian matrix. Let us denote these matrices as B plus C. So where B equal to 1 by 2 into A plus A star. To prove the matrix B is a Hermitian matrix, we have to prove that B star or B conjugate transpose equal to B. If this property satisfied, then we say that the matrix B is Hermitian matrix. So here B star equal to B conjugate transpose equal to 1 by 2 into A plus A star conjugate transpose. So 1 by 2 into the conjugate of the matrix A is A bar plus A star bar whole transpose. So 1 by 2 into A conjugate transpose plus here A star means A conjugate transpose whole bar whole transpose. So this implies 1 by 2 into A conjugate transpose is A power A star plus A conjugate whole conjugate is the property A only and A transpose whole transpose is A. So these are the properties. So this is A. So 1 by 2 into A star plus A. So B star equal to B. Here we have applied the definitions of a conjugate transpose matrix, that is B star equal to B. So that's why we say that B is Hermitian matrix. Similarly, we have to prove that C is skew Hermitian matrix. Let us take what is C here. C equal to 1 by 2 into A minus A star. So take C equal to 1 by 2 into A minus A star. Now find if we prove C star equal to minus C, then we say that C is a skew Hermitian matrix. So C star or C conjugate transpose equal to 1 by 2 into A minus A star conjugate whole transpose. So this implies 1 by 2 into A conjugate minus A star bar whole transpose. So this is 1 by 2 into A bar minus A star means A conjugate transpose whole bar whole transpose. 1 by 2 into A bar minus A transpose whole bar whole transpose. 1 by 2 into A bar minus A bar whole bar is A only. So this is A transpose whole transpose, and 1 by 2 into A bar transpose minus A transpose whole transpose. Now apply the transpose. A bar whole transpose minus A transpose whole transpose. Again C star equal to 1 by 2 into A bar whole transpose is A power theta minus A transpose whole transpose is A. Now take minus common, 1 by 2 into A minus A star. So what is C? C is 1 by 2 into A minus A star. Now we got C star equal to minus C. 1 by 2 into A minus A star is C. So minus C. The property C star equal to minus C is satisfied. Therefore, C is skew Hermitian matrix. Therefore, every square matrix can be uniquely expressed as sum of Hermitian and skew Hermitian matrix. 1 by 2 into A plus A power theta or A star and 1 by 2 into A minus A power theta or A star is symmetric and sum of symmetric and skew symmetric matrices. Now, this is example of the matrix A can be uniquely expressed as sum of Hermitian and skew Hermitian matrix. So, this is the given matrix. So, the Hermitian part of the matrix already we proved that 1 by 2 into A plus A star. So, this is Hermitian matrix, and 1 by 2 into A minus A star is skew Hermitian matrix. So this is an exercise for you. Find Hermitian matrix 1 by 2 into A plus A star and also find 1 by 2 into A minus A star. After that, sum these two matrices 1 by 2 into A plus A star plus 1 by 2 into A minus A star. Then we will get the matrix A. This is the matrix. So today we have discussed about various types of complex matrices and their properties and the theorems on real and complex matrices and the problems on theorems. In the next class, we are going to discuss about the elementary transformations and different methods to find the rank of the matrix. Thank you.